Hello and welcome to the monthly interview program that features outstanding members of the mineral community, including collectors, dealers, artists, photographers, and more. We aim to shine a light on the lesser-known mineral people that certainly deserve to be shown. This program is presented by the Young Mineral Collectors. I'm your host, Matthew Parshchikov from Cologne, Germany, and this is Under the Radar. Hello everyone, welcome back to the show. Today we have another young scientist who is a postdoctoral researcher at the Carnegie Museum of National History in Pittsburgh, Pennsylvania. He helps identifying new minerals and their crystal structures. And he also collects very cool and though small but very special minerals. Because may it be because of their beauty, because of their crystal structure, or because of their very long and very interesting crystal formula. Please welcome my good friend Dr. Chris Emproto. Hey Chris, how are you doing?
Hey, how's it going, Matt? Glad to be here.
Happy
It's a
to have you on the
beautiful
show.
Saturday morning.
Yeah, this is great to have another scientist on the show. So let's just start where I always start. How did you come into collecting, and how did you decide that you have a passion for minerals, and you eventually became a scientist and a doctor?
So we've talked about this in the Discord if there was not a collecting gene. And I'll say I feel like there's pretty good evidence for there being a collecting gene with my family. My dad is a very big collector, but not of minerals, of guitars and basses, especially ones that he constructs himself. So he does like all the assembly and like soldering of the wire and everything. He's got over 300 of them. And so he also collects model cars and also collects life-size cars. And so he's very much a collector. And I don't know if that just like subconsciously affected me growing up, where I was like, oh, yes, I'll collect things. But I just naturally gravitated towards collecting natural objects. So I really liked fossils, I liked shells, and I, of course, liked rocks and minerals. And so I was just collecting all these different natural objects. And over time, it just kind of dropped off in my interest in like shells and, you know, bits and pieces of marine life that you get at gift shops and stuff like that. I was like, nah, I'm really not interested in this anymore. Even though I really loved like marine biology and ecology and whatnot, and just eventually narrowed my focus on minerals. And like we all start collecting pretty much like whatever we can buy. And it took me a long time to develop sort of like a taste and a purpose in my collection. But that came from like a few very important mentors. So I'd say like very much influenced me as a collector, turned me into like a serious collector and a focused collector. And by focus, I don't mean that I'm focusing on something extremely specific, like, you know, minerals from Colorado or something like that, but really just like focused in the things that I want to add to my collection. Like, does this fulfill like a purpose for me having it? And that, which I'm sure we'll get to and cover later, is like, does this thing tell a story and connects to my interests and why I love minerals? So some of the people that were really important for me as like a younger collector were like my dad, of course, who supported, like both my parents honestly like supported me in my collecting, like taking me to museums and whatnot. But there was a collector and dealer who lived on Long Island, where I'm from, called Joe Fralick. And I met him kind of in his sunset days. He was like a pretty big collector in his day. There's like a mineralogical record issue on his collection. And he's the one who really first taught me like, this is how you pick a nice specimen, like what to look for in terms of like damage, aesthetics, like overall quality. And those aren't necessarily things that reign supreme for me now, but what he really taught me was like, you're like, when you're going to look for these things, just and you have all these specimens in front of you, really just like take it all in, look and think hard before just grabbing one. Don't just grab a piece out of the bin. Don't just grab the biggest one or like the shiniest one. Like this is how you look for something that's actually a good specimen, because a good specimen is one that you're going to appreciate years and years from now.
Absolutely.
So yeah, he was like my first big influence as a collector in terms of like turning me into a very serious collector. He was also very generous with me and sold me things for way less than I think he was offering them for on his eBay store or to like other collectors. So that was huge for me to get a bunch of really nice things, many of which I still have, you know.
And how old were you
So,
when you first started like collecting rocks?
uh, so I guess I think of it as like, okay, I was 8 years old when I got my first like specimen, so a rock that I didn't just pick up outside in my backyard or something like that. So I think of myself as like, okay, that was when I was about 8. And I remember specifically the thing that I would consider my first specimen. It was one of those Moroccan aragonite
Hmm.
clusters.
Yeah, yeah. Do you still have that?
And no, I'm not like the most sentimental person. There are a few things that I have that are like very sentimental, like gifts from some of my like friends and whatnot. Those are sentimental, but something like that, where like this thing was really beat up and it was really cool, but I'm not like, oh yeah, I'd love to have that back because it was like a
Yeah.
beat up aragonite cluster from Morocco, and ultimately it being number one in my catalog, or I guess that wasn't number one because I had started my catalog by going left to right in my first iteration of my display case, but it was basically like my first specimen. So I guess it's been just over 20 years that I've been collecting.
Wow. Nice. How old are you now?
28.
Wonderful.
So
Yeah. So you eventually shaped your focus in picking a specimen. Now tell us more about how you shaped your focus and what exactly your focus is, how your what your criteria are.
yeah. So this is all that talk about aesthetics and beauty and damage or whatnot is very ironic from someone who has the moniker of Dr. Crust in our community. But really, so I don't really view minerals as art. I know that's like a very common sentiment, and there's nothing wrong with that. I mean, we all see different things in them, and I tell this to people all the time. So when I'm meeting new people, I'm like, oh yeah, I'm like really into minerals, and someone are like, oh cool, I like rocks. You're a geologist, you probably think my rock collection sucks, and I always have to say like, listen, the most important thing about your collection and the things that you collect is that they are meaningful to you. And when you're a very serious collector, you might be searching for things that are like perfect or beautiful or whatever, because that's the part that's really meaningful to you. And I really like that about minerals. I have many very, very beautiful specimens and some like things that are like common that I just thought were beautiful or interesting looking or whatever. And I also have some things that are like really tiny colorless chips on black carbon tape that you would sooner separate me from one of my fingers than take one of these things from me, because those are also like very meaningful to me for some of the other aspects of minerals that I love, which is their chemistry, crystal structures, and also just like my experiences having been part of this community. So some of those things are like gifts from scientists that I'm very good friends with. I've been very generously gifted like pieces of holotypes, or rather, these would technically be like co-type specimens and whatnot. And those are like, one, literally irreplaceable, two, like very cool as scientific objects. Like, oh, this is a piece of one of the specimens that was used to describe a mineral. And then three, like it being a gift from someone like that gives that piece so much meaning to me. But then I also have my own interests in minerals, like their chemistry and crystal structures, which I'm currently exploring in my job as a postdoctoral researcher at the Carnegie Museum of Natural History in Pittsburgh, Pennsylvania. And so there are some things that are like crusts or chunks or chips or whatever that really like their aesthetic beauty is limited to non-existent, but those are also very deeply meaningful to me. And it took a while for me to appreciate those sorts of things. So if you, in your question, as you said, like, yeah, like how has that changed, or like how did I get those sorts of collecting criteria? When we all start out, where many of us are drawn to rocks because they're very beautiful, and that definitely got me interested in them. Like, is these things are beautiful and natural, and how did they form? Because at the end of the day, like they're just rocks. There's nothing written that says that they had to be beautiful or perfect or whatever. Like, it's just essentially like random chance that some of these things are incredibly beautiful to us. So I just was interested, like, hey, these are natural objects. They're beautiful, interesting. They tell stories. I love that. Geology is all about trying to understand stories. And so that was just really intriguing to me. And then I started collecting, and I was just blown away by like the variety of minerals. And again, it's not just like the color or the forms or anything like that, but just the fact that there were so many minerals. We just officially this winter passed 6,000 approved mineral species.
Oh, fantastic.
Yeah, which is crazy. And so it just blew me away. Like there are so many minerals with all these chemistries, all these structures occurring all over the world in different like associations. Like sometimes you'll find this mineral with this other mineral in this other environment. It occurs with these completely different minerals. There's just like honestly an incomprehensible variety. And so then I started getting more into like systematic collecting, but I've never been a box checker. Like I would never say like I have to have every single monazite species. I have to have every single rhabdophane species. I have to have all the amphiboles. Like I'm not a box checker. There are some times where I'm like trying to get specific ones, or maybe trying to fill out a group. Like I was very happy to get all three silver, like simple silver halides, like iodargyrite, chlorargyrite, bromargyrite, just because I think that's cool and there's like a cool little sub collection. But I'm not like a box checker. I'm not like I don't have this species, therefore I have to have this sample. Like that's not fulfillment for me. There are ones where it's like, hey, this mineral is really weird, or it has this sensational structure, or it's just like an extremely rare mineral. That's when it's like, okay, this is very cool. I would like to have a specimen of this. Because with 6,000 minerals, and you know, I'm not super rich, so I can't just buy every super rare thing that comes onto the market. Like there are some that are extremely rare and sought after. And so if you want a sample of that, you better be prepared to shell out like $1,000 or more for a chip that you barely can even see. And you have to know the right person who is even offering the chip, and you have to have established a rapport, aka like spent a lot of dough in the past, to be the first person that they think of, because there are a lot of other people out there who would like to have that mineral too. And so it's just like I'm not really about that. Like I definitely try to get the best stuff that I can, but I don't obsess over that. And now I'm definitely moving away from like aesthetic display stuff because of my association with the museum. So trying to avoid conflict of interest. You know, I'm getting things mostly that are of interest to me for research. Things that like, hey, maybe the crystal structure of this could be determined a little bit better, or this is material from a place that I'm very interested in doing research on. That's really what my collection has moved towards. Uh, I mean, I am allowed to have rocks being associated with the museum, but obviously for like conflict of interest reasons, even though I'm not the curator, I work very closely with the curator. Um, I can't be like collecting things that would be seen as like in conflict with the museum's interest in getting the best stuff for their collection. But this is also a really great
Can you
opportunity
explain
for
that a
me.
bit more?
Yeah, of course. So uh, I really want to stay in the museum space because I love being around mineral specimens. That's why I collect mineral specimens, is because I love being around them. I love looking at them, like studying them, like doing analyses. Like I love all that. That's why I collect minerals. And a museum has a mineral collection, including many things that they want to display or like have for research purposes and storage. And when you are a curator and you're responsible for like acquisitions and deaccessions, so like getting rid of stuff, you would be in conflict with the museum's interests if you were also like a very serious collector, and there would be ethical concerns because if you're as a collector trying to get the best stuff for your collection, but also it's your job to get the best stuff for the museum's collection, that's a conflict of interest. But like if you're out collecting your own rocks, like doing research on them, and then still like acquiring good like
Okay,
display
I get you
quality
now.
pieces for the museum, those are not in conflict. So like you're still allowed to have rocks. It's
Okay.
just you're
It's a
yeah,
role
you can't
conflict.
be
Yeah. So if you see a good
yeah.
rock and you decide, okay, do I want to buy that for the museum or for myself? Okay, now I got you.
Yeah. So anyway, that's another reason why I've just moved away from like display sorts of things is even though I'm not responsible for adding things to the museum's collection, like I love my job and I don't want to have even like the appearance of a conflict of interest, but I still have that sort of energy of still wanting to get these really amazing specimens. And now I could just redirect that. And like the museum has a bigger budget than I have for mineral specimens, and it gets to go in a much nicer display. Like I don't have anything on display. My stuff is all in boxes. And so if I can go and like help find a really great specimen to go on display in the museum, and then I get to show up to work and I get to see it lit up in the display case with all these other great minerals, like that gives me way more fulfillment than it would be to like put it in a box under my bed. Also, like all the patrons of the museum could come and see that rock and like enjoy it. And that's way cooler again than it just sitting in my closet, sitting under my bed, sitting in my storage unit, whatever. So I still have that same energy and passion. And honestly, I'll say the skills of having looked at and like been in pursuit of like what I think are good minerals for so long is like I don't necessarily have to learn that stuff from nothing. Like I can just continue to keep getting better at it and offer my advice on what is and isn't a good specimen or a good price to pay for it, plus all the contacts that I've made. So I'm really actually quite happy with this arrangement. It's something that's hard to understand when you're just a collector and you haven't like stepped into that role where you would potentially be asked to stop collecting, but it's absolutely one, it's not the end of the world, and two, it's like I get a deeper fulfillment out of searching for these specimens because it's like it's just a much greater purpose to be able to get something for public display than for my own private display because I just love sharing my passion for minerals. And so my favorite parts of my collection are when I can like share that with people, like when I have like friends over and like we're going through my minerals and I get to tell all these stories and why I love this specimen or why this mineral is really cool. So it's like that's really where a lot of the fulfillment comes for me. I don't have things that just sit under my bed that I covet and I will not show anyone because it's like my own guarded treasure. Like I'm not like that at all. I love posting my stuff on Mindat. I love like showing my friends like mineral specimens. So I think that translates really nicely to the museum world where I can go and do that, except instead of just sharing it with my friends, I get to share it with like the hundreds of people that walk through the mineral display every day.
Nice.
So it's just, yeah, it's way cooler and actually, I would say more fulfilling than searching for things for my own collection. And so it's not even like that collecting bug has gone away. It's just the energy is redirected towards a greater purpose, which is more fulfilling than it was when I was just looking for things for my own collection.
Great.
I've donated things to museums too. So
Nice. Wow. So, why don't you tell us about how you decided or when you decided to become a scientist and why you studied geosciences or geology and what your dissertation was about?
yeah, absolutely. So I don't know if there was a time where I just decided I wanted to be a scientist. It wasn't like, oh, I was sitting in a classroom and I just was like, oh yeah, I would like to be a scientist. I just always wanted to be a scientist. Like I was just born a nerd. There's no other explanation for it. And so I just always wanted to be a scientist. That was always my plan. I was always like obsessed with science. Like when I was younger, I would just read reference books.
Oh,
Like it
wow.
wasn't even, yeah, it wasn't even like, oh, like nonfiction, like narrative nonfiction or anything. Like, no, I would read reference books. Like, here's where this species of frog is found. Here are the visual characteristics of the painted turtle or like box turtle or whatever. I obviously don't remember very much about all that stuff, but like that's the stuff I would read. It's just like like scientific reference books about like reptiles, fish, like rocks, obviously.
Yeah, I get you.
Just yeah, like that's what I would read. And I just loved it. I was like a sponge for information. And I was just always, I wanted to be a scientist. Like I said, I had a lot of interest in marine biology as well, because I loved sharks and fish and just marine ecology. Like it's very complex and beautiful. And then I was like, yeah, I really hate doing dissections and like the internals of these organisms doesn't really excite me. I'm not like, oh wow, I wonder what the spleen of this fish looks like or something like that. I'm just like, ah, yeah, no, I don't want to have any part of that. And that's an important part of biology. And so that kind of turned me away from biology. Like I wasn't really interested in the squishy parts. I liked how things interacted with each other, but wasn't really interested in the squishy parts. And like rocks don't bleed.
Yeah,
And I was just more interested in rocks and minerals anyway. And so it went from like wanting to be like a scientist to potentially a veterinarian slash like marine biologist. And then I was like, yeah, no, rocks, that's where I want to be.
great choice.
And so by the time I was in high school, like I wanted to be like a mine geologist, probably. And so I was looking at some schools and ultimately decided to go where it made the most financial sense and then studied geology as an undergraduate at a place called the State University of New York at Oswego, which is in northern central New York on the shore of Lake Ontario. Beautiful campus. And I just remember the moment that I wanted to pursue a PhD was my in one of my first introductory geology courses. And I was so stoked to finally take like a geology class because you learn a little bit about earth science when you're in middle school in the US. And not to like say I was like a know-it-all or whatever, but I already knew most of the earth science, like rock related things. I didn't know anything about weather, so that was all new to me. And like some of the other random earth science topics we talked about, like definitely learned some things. But when it came to like, hey, what's Mohs hardness scale? What's an igneous rock? Like those really basic parts of earth science that you learn, I was like, yeah, I'm bored. Like I already knew all this stuff because I just, like I said, would read reference books all the time. And it wasn't until I got to that college course that I was like engaged again with like the learning, but in a way that was totally different. Because when you're reading books, that's a very different sort of way you're getting information than when you're in a college course, like being taught by someone who's like a good instructor.
Absolutely.
That can be like transformative. Having a great professor that can just explain things in a way where you can connect all of those things together and like then synthesize new thoughts. Like so that was huge and that like totally engaged my brain in a way that it hadn't been for a while. And I was just like, I want to get my PhD. Maybe I want to teach mineralogy. but I want to go get my PhD so that I can continue this like lifelong journey of learning and become an expert in what I love. And so, yeah, I just remember that exact moment. I remember the room I was sitting in, the part of the room I was sitting in, and it must have been one of the first ones because I eventually changed my seat in that class. So it had to have been like first week or so of that intro geology course when I was like, yeah, I want to get a PhD. And I'm still friends with that professor. He actually virtually attended my dissertation defense,
Oh, nice.
which we will get to. Yeah. So he said like, what was my PhD on? So there was another step in between that and my PhD. So that professor, who is like a close mentor and friend and my undergraduate advisor, uh, he knew my master's advisor. And so he was like, I know someone that you're going to get along with. He's also really into minerals. He's a great mineralogist. And I just know that he will be a great mentor for you. And so he connected me with my master's advisor, and we really clicked. And through some like coincidences and a bit of bad luck and ultimately a bit of good luck that I won't get into now to save some airtime, I ended up being able to go and study with him at Miami University in Ohio. So his name is John Rackavan. Some of the people in YMC may know him. He's currently the curator at the New Mexico Tech Mineral Museum and the state mineralogist of New Mexico. But he's also a very prolific science educator. He's done a lot of lectures, written a lot of articles, whatnot. And so I was so stoked to go and work with him and learn from him. And again, it was like he just totally engaged me in a way that I hadn't been in so long, where my brain was like a sponge. I was just absorbing everything that he said. And he taught me so much about mineralogy and just really shaped the way that I think now, and just completely accelerated my learning and turned me a lot more into the scientist that I wanted to be. So
Great.
yeah, it was
It's
like a
always great to have
yeah,
someone
fantastic
who's
time.
leading you, a mentor. Yeah.
Yeah, and so he wasn't just a mentor in terms of like my science, but also in like collecting as well. So he has a very good collection. He's very knowledgeable. He's a great eye for minerals, and so my collecting was also accelerated significantly under his mentorship. He introduced me to so many people and taught me a lot more about like how to find my focus and understanding like what are the specimens that are the most meaningful to me, and helping me to develop that so that I can be pickier and what I get. And again, not pickier for like reasons of like, oh, I have to have the very, very best specimen or whatever, but it's just like this is one that I truly like that's meaningful to me. I'm not just buying it out of some obligation, like I have to have one of these and this is a cheap one or whatever. So yeah, he's just a great mentor. And then after my time there, I was also interested in like resource geology. So I was doing more of like applied mineralogy with John, where I was doing like X-ray diffraction and understanding the chemistry of apatite from a type of a very unusual igneous rock called a crustal carbonatite that happens when you melt a limestone when a mountain belt collapses. And so that was like pretty specific, but really like applied mineralogy. And I was like, I'm interested in applying mineralogy to some other problems. I'm interested in like renewable energy. And so for my PhD, I decided to apply what I had learned about how minerals form, how they interact with each other, where the ingredients come from, how they combine, to understanding the formation of resources that we need to transform our grid to sustainable energy, like green energy. So things like lithium and copper, we need lots and lots of copper. Copper is ubiquitous in electronics. We need lots of copper wiring to make solar panels, to make wind turbines, to make electric vehicles. We need lithium for lithium ion batteries, for like our cell phones, for laptops, for electric vehicles. Like these are pretty important if we want to actually have a sustainable grid. And where we're at right now, we still rely a lot on fossil fuels. And if we want to get to the point where we are not relying on fossil fuels, like the only way out is through. And so we have to mine a lot more metal and we have to get better at reusing the resources that we have already mined. And so what I was doing was just one part of this is that even if we reuse everything that we had ever mined, we need a lot more copper, just for like one example.
Is there that amount of copper, is it available on the Earth?
So it's really interesting that you asked that. My doctoral advisor had written a paper where they were trying to model that. And there are a lot of questions, but it is looking very difficult. That the discoveries are slowing down, they're getting smaller, and our demand for copper is increasing. And so there's probably a lot of different aspects to the solution. It's not like we will just solve all of this by mining more or by using less. Like we're going to have to do everything possible to make it work. But yeah, it's a really interesting topic, but just finding the resources is one part of that. And then there's like how do we extract this very efficiently? And so there's not one piece of the puzzle that's like the most important part or anything like that. Like we all have to contribute our own bits to make things work. And there's a lot of incentive, economic and humanitarian, for making things work. So I do have faith that we will make something work. Like we're not just going to get to a point where we're like, well, can't make any more of these. We're just going to give up. Like people aren't like that.
Yeah.
We're resilient. So I was just very interested in like, okay, how do I apply this to something that I think is world changing, like getting enough mineral resources to make the renewable energy technologies that we want and need. And so, uh, I was just mentioning to you before in our conversation beforehand, people have walked like all over the earth and we've found a lot of the easy stuff, like things that you could just find by walking around, picking up a rock. Oh, this looks like it has copper in it or gold in it or whatever. That stuff has been pretty much mostly found. It would be very surprising to find like another really good deposit just at the surface. They're probably still out there, but there are way fewer of them than there were 20, 30, 100 years ago.
Yeah.
And so a lot of the deposits that we are finding are found by doing like geophysical surveys, looking at, okay, this looks like there's something going on here that could be like mineralization or whatever, and then drilling. Those are really expensive. And also, it'll get to the point where we've exhausted the things that we can find with just those technologies. So like not every deposit has a really obvious geophysical signature,
Hmm.
especially some of these like the lithium deposits that I was working on as another part of my dissertation, like unrelated to the stuff I was doing with the copper. But like that's just dirt that has more lithium in it than other dirt. Like you can't detect that geophysically. You have to drill it and like
Yeah.
do a chemical assay. And so that's where other tools come into play. And that's what I was working on, where these things are like geochemical vectoring tools. So like chemical signatures in minerals that we can look for and use to say this area looks promising, this area might not be promising, etc. And so I did stuff with isotopes. So that was what I was looking at with these copper deposits. So I was looking at a very specific type of copper deposit that's very anomalous and poorly understood because there is just so much variety that it's really hard to say, hey, these all form from this one process, because they all have these things in common, but there are just so many different flavors of them that it's hard to just say like, okay, if they all form from the same process, like why do we have so much variety? And where does that variety come from? And that's just been really contentious in the literature. And so we were trying to use isotopes to trace, okay, do they all at least have the same metal sources in common? Like, is the copper coming from the same place? Sorry, I didn't mention, these are called iron oxide copper gold deposits, or
Fantastic name.
IOCGs. Yeah, because they're just named after the things in them, iron oxides, copper, and gold. And so we're just wondering, okay, is it just that the metals are all coming from the same place, and like the fluids that carry them are all coming from the same place, and it's just like the different rocks that those are being deposited into is what's giving these different flavors, or different, like, depths of mineralization or whatever. And so we're just going to use the isotopes to trace that, because different like processes will give different isotope signatures in the metal. So for example, if the metals are coming off like a magma and like going right into like dissolved in like a fluid, and then that's put into a rock, that iron is going to be pretty much unchanged isotopically from the magma. Whereas if there's just like a fluid coming and like leaching iron out of these rocks, and then that is being carried and then deposited in like a shear zone or something like that that's channeling the fluids, that will give a very different isotope signature based
Hmm.
on like a whole body of literature. Like, those were our hypotheses. And so I was developing titanium isotopes, which titanium isotopes are a really like pretty cutting edge method of understanding rock formation. And they had really only ever been applied to like igneous and metamorphic rocks. Because people are like, hey, titanium is really insoluble. Like, if you had titanium dissolved in something and like you change the acidity, it'll just like drop out rutile, like little tiny rutile particles, just like that. It's really hard to keep it dissolved. And
Okay.
so for a while, people were like, also titanium is set in such low concentrations in like groundwater, seawater, all that. It's very insoluble. And so people are like, titanium's insoluble. It's not going to go anywhere when you have like fluids moving around.
Oh, but with
Like, we're
isotopes,
good. So with the isotopes, so if it's not moving around, the isotopes aren't going to change, because to change the isotopes, you have to separate the light from the heavy isotopes.
yeah.
And so we were like, well, what's happening in mineral deposits? Because in mineral deposits, especially ones that are made by hot fluids, like depositing metals, which is how like pretty much everyone who studies iron oxide, copper, gold deposits thinks they form. We disagree on where the metals and fluids come from, but we ultimately agree there are metals dissolved in fluids, and then that drops out IOCG mineralization. And so we're like, hey, if you're moving around like millions of tons of metals, like you've got a lot of chemical tools to like grab and hold metals. It's not a crazy idea to think that you might have better chemical tools to pick up titanium than like groundwater would. And so we decided to measure some titanium isotopes in magnetite from these different mineral deposits, and we just got crazy Well, crazy implies that they're like not realistic or something. We just got numbers that no one had ever seen before, like fractionation, like separation of heavy to light isotopes that
So
was like
how many isotopes are
three
there?
of titanium. There are, let's edit this if I say it wrong. I think there are
Yeah,
five
that
stable isotopes.
okay, yeah,
Yeah,
that wasn't a serious question. Okay.
yeah. Titanium doesn't have any like extremely rare isotopes. So like hydrogen, for example, most hydrogen is just called protium. It's just a proton. And then there's like heavy hydrogen, like deuterium, that has a proton and a neutron. And then there's like tritium, which is unstable, if I remember correctly. And deuterium is really rare. Tritium, I think, is a nuclear product. So like most hydrogen is just like hydrogen one, which is protium.
Yeah.
And titanium doesn't have any like super rare
Oh,
isotopes.
I
And
forgot
so,
to ask, sorry. For the people that
yeah.
aren't like us,
Oh, yeah.
we know chemistry. Explain what an isotope is.
Yes. So an isotope is a specific combination of protons and neutrons. It is a variety of an element with a specific number of neutrons. So the element type, so gold versus silver, is determined by the number of protons. And so every single atom of lithium in the entire universe has exactly 3 protons, no more, no less. Every atom of hydrogen in the universe has exactly 1 proton. However, as I just mentioned, some atoms of hydrogen can have like 1 or more neutrons. And so that changes the isotope. And because it's the same element, it has more or less the same chemical properties. So hydrogen and deuterium will bond very similarly, but because adding a neutron basically like doubles the mass of hydrogen, that actually really more so than any other isotope difference, because it's like relatively a huge difference, that changes like the bond strengths and whatnot. And so that's why if you drink only heavy water, you will become very sick or die, is because your body is like organisms are lazy. I'll say it right now. Organisms are very lazy. They don't like expending more energy than they have to. Your body is like unable to, break and move around the bonds with hydrogen that it normally can do with the mostly like protium hydrogen, just hydrogen one. Whereas if you have only heavy hydrogen, your body's like, I can't break these bonds. Like this is really hard, and it's like your tools in your body are not going to work right, and you'll die. Whereas
Great.
for like uranium, uranium's really heavy. Uranium has, again, edit this if I forget exactly. So uranium has like 90 protons. I think 92 is thorium. We can look that up later. Anyway, the isotopes of uranium. So uranium-235, that's the stuff that like the government and all the terrorists want because it's fissile. And so if
Government and
you
all the
hit
terrorists.
uranium-2, yeah, no, don't keep the uranium-235 away from the terrorists. That one's fissile, which means that if you hit it with a neutron, it will like decay and then give off more neutrons.
Mm.
And it gives off more neutrons. Those run into more uranium-235 atoms, and it keeps it what is called a chain reaction
Yeah.
going. And that's really good if you want to have nuclear fuel for, in like a fuel rod, because it'll keep going, keep producing heat, and then you use that to make steam, use the steam to drive the turbines. You got nuclear energy.
Yeah, it's not so good if the
Or you
terrorists
can have
get
a,
it and make an atomic bomb. Yeah.
exactly, they have a chain reaction and like, boom.
Okay, so let's
So,
let's go back to the titanium isotopes and
okay, yeah, well,
your
all
your
right, let me finish
dissertation.
this. Yeah, with the uranium, I was just like, oh, yeah, let me just talk about why the terrorists want uranium. So uranium-235 is one of those isotopes, and then uranium like 238 is heavier. There's like a very, very small, like just over 1% mass difference between uranium-235 and 238. And so there's like basically no difference in the chemistry there. Whereas hydrogen, that's like a doubling of the mass, going from 1 proton to 1 proton and 1 neutron. And so extending this back to titanium isotopes, titanium is pretty light metal. And so there's a relatively good sized mass difference between the lightest isotopes and the heaviest isotope. And so we actually see a good amount of fractionation. And this, again, was something that people didn't think there would be any fractionation for a fluid, because they're like, titanium's not going to move. And if it doesn't move, it doesn't separate. If it doesn't separate, we're not going to measure any difference. And we demonstrated that that's just like not true at all. There is a lot of fractionation. We actually saw triple the range of titanium isotope fractionation that had ever been observed in natural materials
Oh
in
wow,
one deposit. One deposit. And
crazy.
so, yeah, this was like really exciting, but also like really scary, because a lot of times you're doing science, you're like, oh, let me look in the literature and see what, this like very influential paper reported on this topic, and you get like guidance and whatever. With this, it was like I go into the literature and people are like, yeah, this doesn't happen. And I was like,
So either
how
you're
do I
completely
explain this?
wrong or you made
Yeah,
the biggest breakthrough.
yeah, yeah. So it was like our first assumption is we screwed up, but we had like replicates and the numbers were like internally consistent. We measure standards too. And so if our like technique of separating the titanium for measurement was what was like driving these numbers, then the standards wouldn't have worked. But the standards were fine. Like the numbers are real. And so it's just, what's going on here? So that was a big part of my dissertation. That was 3 chapters worth of my dissertation. The first was like we measured those titanium and iron and oxygen isotopes as well and magnetite from this deposit in Australia, this iron oxide copper gold deposit called Ernest Henry, which is a pretty big copper deposit in Western Queensland. And so that was my first paper as part of my dissertation. And after that, we were like, well, we put these numbers out there, but we really don't know how to explain them. We know that it's like probably these processes that are driving it because we know that it, based on modeling that other people have done, it cannot be just like igneous processes like a magma crystallizes magnetite, blah, blah, blah. That had been actually pretty well studied, and people had some very convincing models to show that that's well behaved. And that was not what was going on here. We had some very poorly behaved things. And so the next step was like, how do we actually figure this out? And so we did some benchtop experiments and we did some computational modeling to try to predict what direction fractionation would go. So like when like a fluid, like a really salty water, basically is what's moving around metals. When that interacts with a titanium bearing mineral and they exchange, like, and it takes some titanium, is it going to prefer to take heavy or light titanium? Because that direction will inform our model. And so that will tell us if the titanium is being brought in. So if we have really, really heavy titanium signatures, isotope signatures, and we know that the fluid prefers light titanium isotopes, we can say, okay, the fluid took light titanium isotopes away and we are left with the heavies, and then vice versa. So that was what we spent a lot of time figuring out. And then the last one was just applying this to a lot of different types of mineral deposits that we measured magnetite from and trying to make sense of it all and coming up with different fractionation mechanisms. And it turns out there's not just one thing that explains it, because we also saw some pretty crazy numbers in igneous deposits, which we didn't expect. But it turns out that there are other processes that can occur that you do not see in normal, like a regular basalt or whatever, that occur when you have like very massive oxide crystallization. So when you're crystallizing like tons of magnetite or chromite or something, or when you have like magmas mixing and things are like diffusing at different rates, these are processes that don't generally happen in like common systems. And these other research groups have been looking at these like typical systems just to try to understand the basic general behavior. And we were looking at weird stuff. And it turns out when you look at weird places, weird things happen. And so that was the bulk of my dissertation. And then the other part was lithium deposits. So I was looking at lithium clay deposits in Nevada and trying to better refine the model for how that deposit formed. Like the lithium clay started off with like, 0.3 weight percent lithium, which is like really good for a lithium clay. Most of them are 0.1% or less for like good ones. And then it like got hydrothermally cooked and upgraded to like closer to like 0.8 weight percent, something like that. So it just like got cooked and super upgraded, which is crazy. And so I just did a lot of like mineral chemistry work, trying to figure out exactly what was going on there. So that was my dissertation, just applying mineral chemistry, like how do these form? Where do the ingredients come from? What does this tell us about the geologic history? How do we use minerals to understand their environments, basically, and applying that to our understanding of resources that we need for things that we want to make for a sustainable grid. So that lithium deposit I worked on, like they're going to start producing lithium, I think, within the year or by early next year.
Wow,
And so there very well could be
fantastic.
lithium in battery electric vehicles that I see on the street like a year or two from now from this deposit that I worked on. So that's really cool to
Oh,
me.
so this is really like you did this. This is a breakthrough also, and you are a part of something. I'd say it's pretty big, yeah. So congratulations on that. And
Yep.
you're just
Thank you,
28
man.
years old. I mean, young people,
Yeah.
you can do this too.
Yeah, honestly, studying geology has been the most rewarding thing for me. And always was just like, I'm going to make this work no matter what. I can't imagine doing anything else with my life. And so I'm just going to keep going down this path and making things work. And I'll take the next chance and like keep going. And I've been so fortunate that things have worked out for me. But
Great.
that does happen for like people who are determined and work hard. Like you'll make opportunities. And like I've had to work hard. I'm not the hardest working person or I was never the smartest person in my class, but I had this like combination of things like where like I worked hard and I was genuinely interested in what I was learning. And that has been a recipe for success for me that I'm just so grateful for like all the opportunities I've had and been able to take advantage of, like all the mentors, like people want to help, people who like share their interests and who they, you know, see like, good things in the future for. And I've been so fortunate. People have taken me under their wing and taught me so much. So I really just wanted to mention like some of my mentors along the way because I really would not be here without them and like them encouraging my growth as a person and a scientist, but also like connecting me with other people so I can continue my journey. Like that's really just how I've been going one place to the next. So really, like I think anyone can do it if you have the passion and the drive.
Exactly. This is
Yeah,
continue what so to everyone watching right now, obviously, continue what you're doing, continue to your passion for minerals,
yeah,
for whatever you're doing. Yeah, and you can also you can achieve anything with passion.
yeah. I mean, I don't want to leave off without saying like I have had the incredible privilege of like, I grew up in a stable household. My parents always supported my interests. They never told me like geology is stupid, like you should be an accountant. So my family has been so supportive, and like I was like very fortunate. I was able to go to college with like scholarships and like a college funds. So I came out with minimal debt. And once also, it's worth noting for people who don't know, going to graduate school for geology, like 99 times out of 100, you get paid. Like you have a stipend and you may have to work for it. Like I had to teach every semester of my master's for funding. And I had to teach just under half of all the semesters I was there for my PhD for funding. But if you get through undergrad, going somewhere that just gets you out with minimal debt because it's just not worth it going into 160,000 US in debt. But once you get to graduate school, like it's a much more level, financially level playing field. Like, yeah, I didn't earn great money, but I didn't want for anything. Like I had a stipend. I like I was surviving. It was good. So just yeah, for people who are out there who have dreams of becoming a geologist, like don't be intimidated by graduate school because you shouldn't have to pay for it. And that opens up that opportunity to so many more people. I think that's a really, really good thing that a lot of fields, unfortunately, don't have the funding for. So
Yeah,
yeah,
great.
go out and get it.
So now let's switch to rocks. Can you show us some
Yes,
of your yeah, you've earned your nickname, Dr. Crust Emproto. Now, let's
yes.
why Crust?
So I don't just collect crusts, but I collect a lot of things that, again, don't really have much in the way of aesthetic value. But I also love micro minerals, and so micro minerals sometimes there's like they're crusts, but you need a microscope to appreciate them. And luckily, I have a microscope, so I love micro minerals. But I also have some that I can't even really see with my microscope, like little chips of things that are more like objects of scientific intrigue. But I'll show some of the various things that I have in my collection that I think are just very cool and maybe representative of what I love about minerals. So I guess as Dr. Crust, and I will never make anyone call me doctor. Uh, as Dr. Crust, I will start off with a crust. So let me turn my camera. So how's the lighting? By the way, this is a piece of the Odessa meteorite that fell in Texas that I received as a gift recently. It's really heavy octahedrite type iron meteorite, but I was using that to prop up my phone. So yeah, we'll start off with a crust. So this is a Nikenichite, which is a really rare arsenate. This is from the Tolbachik volcano. And this is a very, very good example of this mineral. It's beautiful under the microscope. I unfortunately do not have a photomicrograph of this one, but this is a good crust. It's
This
a
is a
really
nice
rare
crust.
mineral. This is from like the best of species find of this mineral. Like these are fabulous. They are so richly crystallized. It's one of the arsenates, and so it's stable. Some of the Tolbachik minerals, unfortunately, will goopify if you do not store them correctly.
Oh,
There are actually some that are extinct in the wild. So they formed at these like gas vents, volcanic gas vents called fumaroles, where there's hot gas coming out, and that gas has like metals dissolved in it, almost like metal steam. And when that encounters the cold air in like because this is in Kamchatka, Russia, so
oh,
it's cold.
nice. Yeah.
Yeah. Yeah. So when that hot volcanic gas encounters the cold air at the surface, those metals, like that metal steam, is going to condense and it condenses in the form of minerals. That's what happened here, but there are some that condense like other minerals that were not stable. And so those are essentially extinct in the wild now. Like that when those gas vents go extinct, like the minerals break down because they're no longer like in their stable environment at that interface of like the hot volcanic gas vent and the cold air, and they like break down. And so there are some that have gone extinct, and so the only samples that exist are ones that were saved in museum collections and stored properly.
This is a cool crust.
And
I relate to that crust. I like that crust.
it's a really good crust. And I'll show another one that's not exactly a crust, but this is one that's like people who know me know that I like trash talk pseudomorphs a lot. This is one that I collected myself, and this is one of my
Oh,
favorite
wow.
mineral specimens. This is in my best box. So the blue is linerite, which is lead copper sulfate. That is growing on an anglicite, which is lead sulfate, slash cerusite, which is lead carbonate, replacement of galena, which we know is lead sulfide, which was the original cube there.
Oh,
And so
that's
that's a
amazing.
double pseudomorph. Yep, double pseudomorph. And what's interesting is the rock it's on is also kind of a pseudomorph. So this was a limestone, and now it has been totally replaced by quartz. It's called
Wow.
silicification. And so I collected this 15 minutes after I stepped into the Blanchard mine in New Mexico on a field trip with John Rackavan, my first year of my master's.
That's crazy.
So I didn't even see it on the wall. It was like facing in like that, but there was some other stuff, and I'm like, let's just chip away at the wall, and I like throw my chisel and hammer up, chip some stuff, and that all of a sudden is just like sitting there on the ground, and I was like,
I gotta
"You're
say, that's
kidding."
probably the best linerite I have seen
I've got
because
I've
of its
got a really
shape,
nice one in my single crystal collection.
because of the pseudomorph. That's absolutely gorgeous. I mean,
Yeah,
that's great.
it's like it's aesthetic too. It's like a
Yeah, yeah,
really nice
exactly.
piece. Yeah, perfectly centered cube. So that one's very precious to me because I collected it myself. That's the best mineral specimen I've ever collected, in terms of like a display quality, high-end mineral specimen. Like that's just a really good rock. And also the sentimental value. Like I collected that out on a field trip with my mentor and friend John Rackavan with like some of my other friends. Like, just it's a good rock.
Oh, nice.
This is one I got recently. I don't know if you recognize it. This is a crystal of braunite, specifically braunite 2, which is a calcium rich variety of braunite, potentially a new species. That's something I kind of want to work on
Now
here at the
that's a
Carnegie
big
Museum.
crystal.
It's a it's a big crystal and it's in such good condition. It's not like technically complete on the bottom, but like it's a rock. Who cares? And, like the top part is like perfect. It's lustrous. It's got like the right amount of matrix. It's a good color contrast with the garnet that's also on there. This is from the Enchwaning Tomb Mine.
Yeah, that's
And when I
fantastic.
bought this, it's yeah, I love this rock so much. When I first got it, I like was staring at it for a week. When I first saw this, it was labeled housemanite, and I was like, "Dang, that's the coolest housemanite I've ever seen." And it just like didn't look quite right, but I was like, "That's like really cool. That's way better than the housemanite I have. I'll buy this." You know, it wasn't like a terrific amount of money, like pretty low three figures. And so I was like, "Oh, this is cool." But then it was kind of bothering me for a bit. I was like, "This really does not look like any housemanite I've ever seen. It doesn't look quite right." But I felt like I had seen something like it before. And so I go through like the Kalahari mineral list alphabetically, and I did not get very far because Braunite starts with a B. And I clicked on that and I saw the shape and I was like, yes, this is a Braunite. And then I analyzed it, and yeah, sure enough, it is a Braunite. It's really, really good.
So it's even better than the Horsemanite.
Oh yeah. Oh yeah, way better. Really good Braunites are way better or way rarer than house mites, and these are the best Braunites in the world. There are some really nice Braunites also from Longbon. Alex Vensky
Yeah,
just
yeah,
posted
yeah, yeah.
a really
I've
nice
seen that.
one. Yeah, but these Enchwaning ones are just they're so lustrous,
They're
really nicely
fantastic.
formed.
Love them.
Yes, that's a really, really good rock. So that's another one where it's like it's beautiful, it's rare. I love Kalahari things. There's so many unusual minerals that occur there and high quality. Um, got another one. It's just like a weird thing. So I like also like geologically unusual specimens.
Axonite
So yeah, check out the shape of it though.
from
So
Pakistan.
this, yeah, yep, this is from Pakistan. So
Damn,
well, it looks like a normal axonite on the top, right? And then look, it's like curved.
wow. That's
So
that's
that
crazy.
this is all
Very
one
interesting.
crystal of axonite. Yeah. So personally, so I've asked a number of people, including John Rackavan, like what he thought of this piece, and there's not like 100% consensus, but I'm fairly certain that this is just a weird fought-in. And so
Mm,
I think this normal looking part of the axonite up here was the original like growth of the axonite. And then the as this like open, so this part is milkier down here, which you do see in fodens because there's that breaking and like healing,
yeah, yeah.
and that leaves a lot of gaps for fluid inclusions, which cause the milkiness. And so I think the rest of this was from the opening of that alpine cleft. And so I believe that this is actually a fodden, but it is so strange.
It's very funky. I like that. I love
Yes,
Axonite. Axonite is one of my favorite minerals.
I love it too. Hey, you got to come to the Carnegie Museum. There is a superb Russian axonite.
Like huge and jammy.
Yes, huge, gemmy, perfect, perfectly centered aesthetic on matrix.
Someday definitely.
Yeah. So this is one that can't fully appreciate right now, but the white stuff on here is a brand new mineral that
A
we are
brand new
writing up
crust.
currently. Brand new crust just dropped. Yeah. So the yellow is all andersonite, which is like a uranium, like sodium, calcium carbonate mineral. And the white stuff is a brand new mineral. It is the natural equivalent of the chemical compound magnesium selenite hexahydrate. So MgH2O6 SeO3.
Sounds
And
soluble.
there are crystals in here. So it's very lightly soluble in water. It will eventually, over the course of hours, dissolve in water.
Hmm.
Dissolves extremely quickly in hydrochloric acid. I did that test a couple weeks ago when we were doing some chemical properties. But this is like the first one that I found. I wasn't the first person to notice this. A collaborator had like noted that there was a magnesium selenium phase on one of the samples, and I didn't know I didn't even actually see that part of the label. I was just trying to get the associated minerals for this other specimen that of this new mineral from the same mine. And when we're writing it up, we're like, this mineral formed with this like mineral and that mineral and whatever. And I was like, hey, what's this colorless crust thing on here? And I analyzed it. It was like magnesium and selenium. And I was like, that's weird. There are no known minerals that have that chemistry of just like magnesium, selenium, and oxygen. And
Also,
you can't
it's
see hydrogen with the method I
so
was
so
using.
simple and
Yeah.
nice.
So yeah, really weird. And then we ended up being able to separate a crystal of that crust and solved the crystal structure and confirmed that it was identical to that synthetic material. But this one formed naturally, more or less naturally. It formed on old mine walls, but from natural processes.
Oh, okay.
And so, yeah, this was kind of like my first mineral. And so this is not part of that specimen that we use to describe the species. This is another one from my boss's like material that he had collected that we were like just looking at. It's not, they're not like part of the museum collection yet or anything. When we make the holotype in terms of like when it's approved and we have the designated holotype specimen that will be deposited as part of the museum collection. But this is just from the stuff that he had collected and brought back. So this is a gift to me. So that's really cool because it's kind of like my first one. And he has the other half of this rock. But
Nice.
that
Very
was cool.
nice.
And then going back, another kind of like red arrow rock. This is a specimen of, there's a couple of them on here, but Redmondite. This is the first mineral that I ever helped to describe,
Oh
was
wow.
Redmondite. And I've been very fortunate to have been included in the studies of minerals from this locality. I didn't do any of the crystallography work except for these two most recent ones that I will tell you about in a minute. But I did figure out the geochemistry. So I used like my skills that I had been working on for my PhD, like where do these metals come from? How are they transported? Why are they deposited in minerals? And I applied that to try to better understand like why there were 18 new minerals here at this locality in North Carolina called the Redmond Mine. And because of that, I was able to write the occurrence section, which is part of the new mineral proposal that you write and submit to the International Mineralogical Association Committee for New Minerals Nomenclature and Classification, who review and approve these applications.
Hmm.
And so because of that, I was a co-author on these new minerals, and we basically reused that occurrence section for all 16 or 17 of them, that have been approved to date. And so I got to be a co-author on 17 new mineral proposals.
Oh,
So that
nice.
was just like super lucky. But
Fantastic.
we actually, as of 3 weeks ago, and actually as of yesterday, we officially have two more new ones from that mine. And so those are going to be written up and submitted soon. And yesterday, we officially solved the crystal structure of one of these brand new ones and also finalized the crystal structure of this other one. And so that was really exciting. So those will be two more new ones, bringing it to a total of, I believe, 19 new minerals from the Redmond mine. So now
Terrific.
I'll get into,
Congrats. Congrats. This
oh,
is
thank
great.
you. So
Just give us
yeah,
a quick scan. We're kind of running out of time.
yeah, I'm not going to go through all of these for very obvious reasons, but I just wanted to show you. So this is my single crystal collection, and I there are two things that I really find myself fascinated with in minerals, and that is their chemistry and structures. And so this box is just sort of like my expression of crystal structures and like their physical form. So I have other things like some of those micro minerals have sensational structures, and that's inspiring as well. But with some of these, you can see these different structures because these
Oh, so
crystal
perfect
forms,
crystallography.
yeah, yeah. So the crystal forms are a reflection of the crystal structure of the mineral. So quartz, we think of quartz as six-sided. Quartz is trigonal. It has three-sided symmetry. And so
Oh
this
my
is a
God.
quartz that has that three-sided symmetry. Uh, you can like dioptase also has it. That one's less obvious. Calcite, so that one's a really nice calcite with So like that modified three-sided symmetry.
What's that purple thing?
This is a purple thing up front here.
Yeah, yeah.
This is a scapolite. So it's not the most tetragonal scapolite, but it is a gem scapolite single crystal from Pakistan.
That's wonderful.
So yeah, I love this because this is just like a reflection of the crystal structures. And I try to get like morphologically like good. Perfect is a relative term, I think, but morphologically as good as possible of an example as I can get of different minerals to showcase like their crystal forms and structures. There are some like it's not very obvious that this crocoite, which I just got on my travels in Australia, it's not very obvious that that's monoclinic, but it's a single crystal crocoite. Pretty cool.
Nice.
This is actually one of the world's best Vaquitaite thumbnail crystals, and this one you can tell that it's triclinic looking at the different shapes of it, of the different angles that the sides meet at. So that is one reflection of my interest, and I'll get to this other box. The other thing I love is the chemistry. And so this box is in more or less Dana order.
Oh, nice. That's cool.
Yeah, so there's some really interesting things in here. It's got some like natives. This is a really special one. This is crystallized Portlandite, which is a mineral that you walk over every day in cement, but it is extremement rare in nature. This is calcium hydroxide, CaOH2.
Oh,
It is
that's
the
cool.
calcium equivalent of brucite. So
Fantastic.
yeah, there's some rare things. I try to have these things have some sort of aesthetic value to them, even if it's like arguable, like this newberryite, which is actually crystallized bat guano. But there are other things in here that like are just genuinely very aesthetic and beautiful. So yeah, there's
Nice.
like nothing wrong with that.
So you have only
Xenotime.
thumbnails.
No, I've got a lot of stuff. So these are just some ones that pack a punch that I think show some of my interests. So there are some
Okay.
very unusual and rare minerals in here as well. Like it's not the most beautiful thing, but it's weird. This gel-like thing called phalliite. It's only ever been found in the Sumeb mine a couple of times.
Nice.
Yeah, really weird. Analyzed it, almost blew it up in the microscope. Yeah, so this to me is like showcasing the beauty and diversity in the chemistry of minerals. And so this is like an educational box for me as well. And like, yeah, there's some ugly ones in here, but I'm trying to get as many different unusual species as I can that you can visually appreciate. And I have lots and lots of micros that are a lot harder to visually appreciate, like super rare things as well. And yeah, while we're almost out of time, I'll finish up with what is doubtlessly my best mineral specimen, which is somewhat well known among some of my friends in the community. So
The ultimate
pardon
crust.
me while I just this is not a crust.
Oh.
So do you know what this one is, Matt? It's from England.
Wait, I know. It starts with L, I think.
Yep.
I saw it recently. The Spans posted it. I forgot what it was. It's from England. I know. Can you? I forgot.
Laracanite,
Yes.
copper aluminum arsenate.
Yeah, it was Lorocanite. Okay. Yeah,
Yeah,
these are
so
superb.
yeah, this is my best specimen easily. I'm never separating myself from this except when I eventually donate it to a museum.
Oh, I thought you
This
when
is
you
just
eventually die, but okay.
yeah,
Less dramatic.
yeah, yeah. This is just like such a good sample of this mineral. It is
Absolutely.
rare. It has a like pretty interesting chemistry and structure. It's beautiful. It's blue. My favorite color is blue. And this is a historic specimen that was probably taken out of the ground in the late 19th century.
Yeah.
So
Fabulous.
yeah, this is like the ultimate specimen for me. And I love this rock so much. And I was very fortunate. I got it in a collection from a friend that I did not pay very much for. I still to this day don't know exactly why he sold it to me because having visited his collection later, one of the things he likes are classic European minerals. And so I don't, I don't understand it, but I appreciate it because this is my favorite mineral specimen and it brings me so much joy to to see it, and I want to eventually donate it to a museum, and I think it's good enough. It might get on display. At the end of the day, like, this is a really good rock, just all around.
Absolutely. Wow. Fair enough.
So
As a
yeah.
last closing question, um, you've done a lot for YMC, and just sum up, what have YMC brought to you, and what have you done for YMC?
Yeah, so I became a moderator last spring, and I was just kind of like an undifferentiated moderator. I was just kind of like helping out with small things, not really doing too much. But when I interviewed, we asked, like, what is your vision for YMC? And I really saw that, like, we want to angle ourselves as an educational organization. And I am very fortunate that I have had extensive training in science education, and collecting. And so I view myself as like this, like, liaison, like this link between the scientific community and the collecting community. And so I want to further our educational outreach goals. And so when I became sort of more of like an official role, when we did a little bit of restructuring, I became the chair of the educational committee. And I had kind of been acting like that. Like, I wrote a lot of the stuff on our Tucson display, like about pegmatites. Like, I did like that writing. I write the articles for most of the articles for our newsletter.
Yeah, and
Um,
also you helped me with the
now,
with under the radar to start off.
yeah, yeah. I'm glad this has gotten off the ground. So I know you had big dreams for this, and it's really cool to see you keep going with it. So this is awesome. Really glad you're doing all this, and it's, yeah, sort of a, I don't know, fulfilling to be on the other side of this thing that we had talked about like months and months ago,
Absolutely.
like actually happening. So yeah, as the chair of the education committee, that's mostly what I'm doing now. Is like, I'm the director of our scientific messaging that includes preparing educational materials, reviewing a lot of our communications as well. So, like, I just kind of like that sort of like wordsmithing and like curating our messages and whatnot. And so that's really kind of what I've been doing, is like science outreach and preparing educational materials and aiding in communications. So as to what I've gotten from YMC, like, I've made so many friends through YMC. It's really just humbling. That was so It's so nice to just be able to, like, you go to a mineral show, and like the first time I went to Tucson, it was actually sort of a lonely experience. I went there by myself, and I didn't really know very many people. And so I was just kind of walking around and like being quiet and like going into different booths and whatever. And it was sort of like a lonely thing. And now you go, like, and now I go, and it's just like, hey, how's it going? Getting a 15-minute conversation with them. Like, two people walk by, like, oh, you got to meet this person. And like, I spend way more time socializing than
Absolutely.
looking at rocks. And it's just like, yeah, I have the time of my life every Tucson, just getting to see all of my friends and whatnot. And then also the community that we have, like, outside of the mineral shows, that we're able to connect with people in like Europe and Asia and like South America, and like all over the world. And like, I've made like really good friends through YMC. Like, I went to Tasmania twice in the last 2 years. And the first time I was going to Australia, like, I've always really wanted to go to Tasmania. It was a place I thought was really interesting. It seemed like there was good hiking and whatnot. I just reached out to YMC, and I just said, hey, is there anyone in Australia, like, that wants to hang out and, like, maybe go rock hounding or hiking or look at rocks or like whatever. Like, I'm coming to Australia. I've got some flexible time, and I just want to explore and meet people. And this guy, Jaron, like, dropped a message. He's like, hey, like, come on by. It'd be really fun to hang out. I could take you out fossicking, and maybe even organize a scratch at the Adelaide mine. I was like, that sounds incredible, once in a lifetime experience. I'm in. And yeah, we just like kept talking and became friends. And I went, and him and his mom hosted me, and they were just like so kind, and like we really like became good friends. And I went back to visit him again this past this past March and April, and had another amazing time. Like he took time off work to take me around like to all these different mines, which I like really appreciated. I brought him lots of like cool rocks for his collection, and also did some photography for him and whatnot. So just like those friendships and connections like that would not be possible without YNC, just have been so meaningful to me. As much as I love rocks, like I said, it's the sharing that's like sharing our passions that's most important to me. Like I love my collection. I love sharing my collection with other people more so than any rock. Like I love having friends who have the same interests and passions. Like that to me is just so fulfilling about this hobby. And one of the most amazing things about our club is it's just a lot of these clubs, these like local clubs, like yeah, they're great for making friends, but like we're a global organization, and it's just so much more powerful than any other club out there, I think,
Absolutely.
that's
You're absolutely right.
currently in existence. So yeah, can't wait to keep meeting people and seeing how the club grows, especially now that we're like a official nonprofit organization, which just seems crazy, but it's really there's cool stuff happening.
It's great to
Like
be
your Under
part
the
of.
Radar podcast.
Yeah, it's great to be part of something huge. Well, thank you very much, Chris, for this fantastic interview. We've been, it's a little bit long, but I think everyone will
Yeah, you
enjoy it.
cut out all the parts where
Nah,
I
this
put the
is so
wrong
much
number of
knowledge. This is so
isotopes.
much great stuff that you talked about today. So thank you very much for coming on the show. I'm very happy that we finally did this.
Yeah, this is great. Thanks so much for taking the time to interview me. This was a lot of fun, and thanks. Yeah, keep doing what you're doing. This is really cool.
Wonderful.
Take care, Matt.
Thank you for watching this episode of Under the Radar. You can check out today's guest through the links in the description below. Tune in next month for another episode, and don't forget to like and subscribe so you won't miss any new uploads. Take care, and we'll see you next time.